We're going to start this one off by looking at the world's cutest killer. So this lecture series is on extinctions, and house cats are a huge cause of that. Not necessarily the cats that live in your house, but cats that were house cats or became feral cats, because those are the larger problem, these cats that feed themselves out in the wild. So 73 animals are killed by a house cat each second. 277 million birds, 462 million worms, 577 million squirrels, voles, etc., 947 million lizards. That's 2.3 billion animals killed in the US each year by cats. I'll talk about this more later in the lecture, but I like this infographic because it uses these really cute pictures to convey this kind of terrible information, but it's something that you can access really easily because of the size and organization of a lot of these features. This is a quote from a scientific study looking at animals killed by cats. We estimate that free-ranging domestic cats kill 1.3 to 4 billion birds and 6.3 to 22.3 billion mammals annually. Unowned cats, as opposed to owned pets, cause the majority of this mortality. Our findings suggest that free-ranging cats cause substantially greater wildlife mortality than previously thought and are likely the single greatest source of anthropogenic mortality for U.S. birds and mammals. The single greatest source. Think about that. This video series is going to cover a series of mass extinction events on Earth. One of the penalties of an ecological education is that one lives alone in a world of wounds. Much of the damage inflicted on land is quite invisible to laymen. An ecologist must either harden their shell and make believe that the consequences of science are none of their business, or they must be the doctor who sees the marks of death in a community that believes itself well and does not want to be told otherwise. I love this quote because it sums up a lot of the kind of sorrow we end up feeling in our environmental science class, is that we come into it excited to learn about all these different ecosystems, and a lot of times we come out of it feeling horrified because you fall in love with these places, these natural phenomena that are occurring all around you, learning about them, and then you learn about this sort of tragic present and future and past, and I encourage you to keep that in mind while also still being wowed and being amazed and not letting that kind of ruin this experience for you. It is a part of it, and I don't think you should ignore it, but make sure you still maintain your sense of wonder. It's the only way to stay productive. A big concept to be aware of during this lecture series is that there is a background extinction rate. Species have always gone extinct and will continue to go extinct throughout Earth's history and evolution. It's a natural process, and there is a sort of predictable or a calculable rate at which that has occurred in the past. There's a lot of variation depending on how you calculate it, so everybody comes up with a little bit of a different answer. We can compare that background extinction rate throughout the history of our planet to current extinction rates and previous extinction rates at specific times in history. So history of extinction. More than 90% of all species that have ever lived on Earth are extinct. So we have had a vast diversity of organisms rise and fall, and that is a natural part of our process as a planet. As conditions change, our populations of species, or our communities of species, also change. Here's a graph from an old textbook we used to use showing the number of families living at a given time in Earth's history. So family is a pretty inclusive term for groups of organisms. If you think about species, you can have many species within a genus and then many genera within a family. So it's a pretty big umbrella. So every time you see a dip here, that is a time when the number of families, so not even just genera within a family or species within a genus, but entire families of organisms go extinct. So each of these points represents a kind of crash, a distinct decrease in the number of families. And we can also look at that in terms of genera. So here's the same information but conveyed differently. So here we see the number of genera instead of families, so this is less inclusive, and how many of those genera go extinct. If we were to look at this in terms of species, it would be even more extreme. So look at these incredibly sharp crashes for our extinctions here, and there's a little one there. So 550 million years ago was the Cambrian Explosion. So early life forms began to flourish on our planet. We start to see diversity occurring in our fossil record. This is a spindle diagram to sort of highlight changes in groups of organisms. So these are all animals and then the protozoa, showing these different groups and how their abundance of diversity within those groups, so either numbers of genera or numbers of species or numbers of families, are changing over time. And so time is going this way, and as those spindles get wider, that represents a larger number of different taxonomic groups within that particular group. And you can see kind of in this pre-Cambrian period, we have all these dotted lines. So fossils are uncertain. We don't have good information, good data for before that time period. Then here in the Cambrian, this is why it's called the Cambrian Explosion, is you see the start of all of these groups really starting to diversify within this time period. So many different life forms sort of arose in the Cambrian. The first mass extinction that we'll talk about happened 444 million years ago. And it's important to mention that a mass extinction is not just the extinction of, a few hundred species or a few thousand species. It's a large percent of the species. And depending on who you ask, that number could be 50% of the total species or up to 75% as a minimum, right? So how do we define that mass extinction? And that happens in a relatively short amount of time. So at least 75% of species lost in this relatively short period of geologic time. So for us, we think a short amount of time is like 100 years, but geologic time, you're thinking a million years. So at this particular time, at the end of the Ordovician, 86% of species were lost. What was happening, they had lowered sea levels. Whenever you have lowered sea levels, you can correspond that with increasing size of ice sheets. So that ocean water is being removed and frozen in sheets generally on land, right? So what was causing that is sort of unclear. It could be the formation of the Appalachian Mountains kind of starting to form. Those used to be the tallest mountain range on the planet. It could be due to a movement of these sort of continental land masses to the South Pole. So if you think about the orientation of our planet toward the sun, the polar regions that are colder because they get relatively less heat energy per unit area. If you move a bunch of the land to those polar regions, you're going to get an expansion of ice sheets because you'll get ocean water forming as ice sheets on those land surfaces. So that could cause those lowered sea levels. Because of that lowered sea level, there was newly exposed rocks that absorbed a lot of the CO2 out of the atmosphere, which could again lead to increased global cooling, and we could go into sort of a positive feedback loop of cooling. That resulted in a short, severe ice age, and most of our small marine organisms died out. Prior to this period, there were many more shallow, warm inland seas. More of the sort of pre-North American continent was in the tropical equatorial region. So if you have a lowering of sea levels, then you would have the sort of shallow, warm, loving sea creatures exposed. So they would then be above the sea level and die. And also the severe cooling could also kill any organisms that needed those warmer ocean temperatures. And this is what the planet looked like. So you can see a really large land mass in our southern pole region. And then here at the equator, we would have pieces of probably what will become North America and all of these shallow inland seas. Something weird happens in the late Devonian, so 375 million years ago. 75% of species are lost, but there's not a huge increase in the rate of extinction. There is still an increase beyond the background rate. However, what we see is a decrease in the number of new species that are evolving. So that's called the origination rate. So this is sometimes called a mass depletion as opposed to a mass extinction. What was going on this time? We had newly evolved land plants, and those were diversifying and kind of spreading across the land surface. This would lead to a decrease in atmospheric CO2, and so that can sometimes cause cooling, right, as we saw in the previous mass extinction. It's possible that these newly formed roots were stirring up trapped nutrients, kind of breaking apart rocks, digging into areas that were not previously exposed, and that caused maybe some kind of pre-human eutrophication, depositing those nutrients into the ocean. And there's some evidence that there were globally large dead zones, much like we see when there's eutrophication today. You see the sediment forms these really thin layers that shows that nothing was living in it, nothing was kind of stirring it up, that bioturbation. And it also forms these kind of dark gasoline smelling layers that show an anoxic activity. So there's glacier formation, which would have caused sea level drop. So anytime we see those sea levels drop, we're thinking cooling temperatures, uniting those two ideas together because of the formation of glaciers and ice sheets. And again, we see many tropical marine species go extinct. This is a projection of what we think the planet looked like around that time. However, I'm not sure if this is just before or just after, because if you look, we still have this large landmass in the south, but it looks like there's been sea level rise since the last time, because you see all these shallow inland seas, and you can tell it's shallow by the kind of coloring that it has. The lighter it is, the more shallow it is, the darker it is, the deeper it is. The next big extinction is the largest extinction known. 250 million years ago, at this sort of boundary between the Permian and the Triassic, 96% of species on Earth were lost. So this is the largest mass extinction on in Earth's history, and it's called the Great Dying. So what was going on? There were huge eruptions in Siberia. So this extended period of volcanism, many volcanoes all going off at the same time for an extended period of time. And the area of Siberia was called the Siberian Traps. So these are regions of volcanism, and if you calculate the amount of lava that covered this area, it was 7 million kilometers squared, approximately, and that would be 1 to 4 million kilometers cubed of lava sitting on that surface. So large amounts of this volcanic eruption, which would also release CO2 into the atmosphere. So beyond that immediate vicinity, having to deal with large lava flows, you would have CO2 and dust and ash being spewed into the atmosphere. Methanogenic bacteria likely released large amounts of methane during this period. So we know that methane is a very potent greenhouse gas. So if we have a lot of volcanism releasing hot gases, dust into the atmosphere, a lot of CO2, a lot of methane, so those are both greenhouse gases, we see a rise in temperatures. And that rise in temperatures would also lead to a rise in sea level. Our ocean is going to acidify due to this release of large amounts of CO2. And when that acidification process happens, we also get this release of a large amount of hydrogen sulfide. And I can actually track that through looking at sediments and the chemical composition of those sediments, because there's particular lipids that will stick around for millions, hundreds of millions of years. And you can analyze those lipids that would only be found in certain groups of organisms. So they're finding this particular lipid that's present in green sulfur bacteria, which release hydrogen sulfide. And it's possible that that would have made the oceans purple, because then there's these purple sulfur bacteria that use that hydrogen sulfide. So a very interesting time in Earth's history. And this was all coinciding with the formation of Pangaea. Whenever you have these large tectonic plates crashing together, you get volcanism and big changes in our climate. Here you can see that Pangaea state of our planet, where we have all of these continents crashing together and forming these mountain ranges, rising up as they get pushed upward as these plates crash together. So this was a huge mass extinction, and we associate it with over 4,000 gigatons of carbon or carbon dioxide that was released into the atmosphere from those volcanoes. If you think about what we've done over the past 100 years or so, that's 100 to 200 gigatons. That's a very short amount of time though, so we would be on track to kind of correspond with that 4,000 gigatons over a period of 1 million years. So we'd see these rising sea levels, rising temperature, a release of hydrogen sulfide, which is toxic to most organisms that do respiration, and a decrease in the ocean pH. So keep these all in mind when you think about what's happening today. 210 million years ago, so shortly after that period, there was another loss of species. And this is another one that corresponds with a low origination rate. So there was a decrease in the number of new species that were sort of arising in this time period, as well as an increased extinction rate. However, it's really confusing to try to figure out why there would be a decrease in the number of new species evolving. So these mass depletion time periods are really mysterious, and there's no clear cause that's been found for why there was a mass depletion here. Potentially volcanism. There was an extinction of more of the vertebrates, which allowed for the dinosaurs to flourish. So that was kind of the outcome of this depletion, but unclear what was going on that caused it. And here's what the Earth looked like, really similar to what we saw before, but we have the movement, the migration of these southern land masses up. All right, so now we have masses in the North Pole region, but most of our land masses are more in our tropical area. So we have these large, warm inland seas. It gets really swampy in this time period. And we do see a rebound of species after these two kind of coinciding mass extinctions. This is the one that most people are familiar with. So 66 million years ago, at the end of the Cretaceous, about 76% of species were lost. We know there was an asteroid impact. So if you look in this region of Italy, there's this the first evidence of the asteroid impact because they found a bunch of iridium in this particular layer kind of within the rocks. And the iridium is really rare on the Earth's surface. Iridium is common in meteors. So you can actually look at the, I believe, percentage or concentration of iridium in those sediments to figure out how large the impact meteor was. And it was about 10 kilometers across, which is huge. So that asteroid impacted, I think on the Yucatan Peninsula is where they found, in Mexico, they found the impact crater. There's also continental shift going on. So a bunch was happening. This asteroid impact might have kicked off this event. However, at the same time, there was volcanism happening in India. So how in Siberia we had that Siberian trap with all those volcanoes. Similar thing was happening in India, potentially at the same time, but it's been hard to get that time frame estimate. But large amount of volcanism happening around the same time period. Whether one happened first, currently unclear. But this was the end of dinosaur dominance. For whatever reason, dinosaurs did not survive this event well, even small dinosaurs. The only dinosaurs that made it out were the birds. So present-day birds are dinosaurs. Dinosaurs didn't go extinct. The large reptilian-like dinosaurs went extinct, but birds still exist, super diverse, so dinosaurs still around. This led to the radiation of the mammals. Mammals survived this event for whatever reason much better. In the ocean, most of the ammonites disappeared, and so this was kind of the big extinction of the ammonites, which were a diverse group of organisms related to squid, I believe. And so we saw a crash in those groups. And now our planet is starting to look more like it is today, right? This is only 66 million years ago, which in our geological time frame is a drop in the bucket. So here's North America, right? I guess I should include this little bit. And then here's Greenland, kind of looks like it does today. We start to see our continents looking more familiar, the separation of South America and Africa, where they used to join together. And we had these large inland seas, which some of these areas we recognize now as large deserts. But this is why if you go hiking around in the canyon lands, you can stumble upon, fossil shells just sitting there, because those areas used to be large inland seas, and then after that you had that glacial movement.